Hi guys, this next section, section 5 of chapter 7, is titled Parts of Similar Triangles. We are going to recognize and use proportional relationships of corresponding angle bisectors, altitudes, and medians of similar triangles. So these are the parts, the bisector, altitude, and median. So if you have two similar triangles, then other parts of those triangles are also going to be proportional. We're then going to talk about and look at a new theorem called the triangle bisector theorem, and I'm going to prove that one for you since it's not as obvious. Okay, so let's start out with the first theorem, special segments of similar triangles. This first one is specific to the altitudes. So AD and FJ are altitudes. That is another name for the height, or heights I should say. And of course that's drawn from one vertex to the opposite side at a 90-degree angle. And we're told that ABC, these two triangles, ABC, is similar or proportional to FGH. And the theorem states that if that's true, then the altitudes of those two similar triangles will also be proportional to the same ratio as the sides of the triangles. Now why would that be true? Well, we know if ABC is similar to FGH, then the corresponding angles are congruent. So angle C and H are congruent, angle B and G are congruent, and of course the angles CAB and HFG, these angles are congruent. But I'm not going to mark those. So for showing this new proportional relationship, let's just focus on these triangles over here on the right hand side that arise from drawing this altitude. So you can see if we have a 90-degree angle here, then the one adjacent forming a linear pair is also going to be 90 degrees. And by the third angles theorem, this angle here will be congruent to that angle there. So you can see we actually have two new triangles that are similar. We have A, B, D is similar to F, G, J, and that is because of angle, angle, angle. And if that's true, then you can see that the sides of these two similar triangles here, AD altitude to FJ is one of the sides of, or corresponding sides of those two new triangles, is going to be proportional to the original sides of the two similar triangles, AB and FG. And for that matter, that will be to the same ratio as DB and JG. Okay, similarly, another theorem here is if we have two similar triangles, and in this case we have KLM and QRS, we're told that they are similar. If we draw angle bisectors from one vertex to the opposite side here, showing that we're bisecting that angle KLM, and we're also going to draw another angle bisector bisecting KRS, then we can see, or the theorem states, that these two bisectors, LP and RT, are going to be proportional to the same ratio as the sides, or the ratios of the two original similar triangles. And the reason for that is quite like the one above it. We have these angles being marked congruent here, and if the original triangles were similar, as we were told they are, then angle M is congruent to angle S, and angle K is congruent to angle Q. So again, I'm going to just look at or home in on these two new triangles over here. I could look at the left, but I'm just going to stay consistent, look at the right. And we know that this angle is going to be congruent to this angle by the third angles theorem. So in fact, again, we have two new triangles that arise. We've got LMP is similar to triangle RST. And again, The reason for that is angle, angle, angle. Well, if that's true, then we can see, just like above, these angle bisectors are now sides of these two new similar triangles. But the original sides of the original similar triangles still has their proportionality, and therefore we could say that the angle bisector LP is to RT as the sides LM is to RS. And we could keep going with that further and say PM is to TS. Okay, a third theorem here is all about the medians of triangles, similar triangles specifically. And remember, a median is when we draw a segment from one vertex to the opposite side, specifically to the midpoint. So here D is a midpoint and Z is a midpoint. And the diagrams show that, showing that AB is being bisected here into two congruent segments. Now, one thing I don't like about the textbook is when they have diagrams side by side, they tend to treat them separately, and I don't like that. So I'd like you to change your notes showing that WZ is congruent to ZX, but they're not equal to or congruent to each other over here. Okay, so we're told that ABC is similar to WXY, so we know all the sides are corresponding and proportional. Now, why are these, well, the theorem states that these medians, CD, are going to be proportional to the original sides, AB and WX. Now, why is that true? Well, if we take a look at it, let's just start out with what we know is true. AB is to WX as BC is to XY. And we can actually, if we wanted to, even throw the third side on there, but I'm going to focus again just on these right triangles. So we know this is true just based on this similarity statement here. Well, we also know that DB, actually I should say twice DB equals AB, and twice ZX equals WX, because they're being bisected, they're being cut into two equal halves. So let's substitute that in. 2dB over 2ZX equals BC, and I'm going to keep the right side of the proportion identical. And the 2's cancel, so we can see here that DB is to ZX as BC is to XY. We also know that if the original triangles were similar, and we were told they are, then the corresponding angles are congruent. So we know that angle B is congruent to angle X. For that matter, we know that A is congruent to W. All right, but focusing just on these triangles on the right, by side angle side, I could say that triangle DBC is similar to triangle ZXY, side angle side. We've got two sides, two pairs of sides that are proportional. We proved that over here. And we've got an included angle that is congruent. So therefore, when we have similar triangles, if we draw that median, again, they are proportional to the same ratio as the sides. Okay, let's see the theorems. So here we have two similar triangles with medians drawn, and we just learned that those medians are going to be proportional with the sides. So let's take a look at JM is to QT as MK is to TR. And we can substitute X is to 5 as 12 is to 8. Cross multiply, we have 8x equals 60. And divide both sides by 8. And we have 7 with a remainder of 4. So that would turn out to be 7 5/10. And here we have a problem with the altitudes of two similar triangles, and we learned that those altitudes are also proportional to the sides. So we have AB is to FG, as the altitude BD is to GJ, 21 is to X, as 9 is to 6. And we have 9x equals 126. Divide both sides by 9. And we have 1 with a remainder of 3, so that would be 14. Okay, now the fourth theorem here is called the triangle angle bisector theorem. This one is much less obvious as to why we have parts being proportional. Okay, so what the theorem states is if we do draw that angle bisector within one triangle here, the other theorems were all about two similar triangles. Here we just have one. And we draw an angle bisector cutting this angle KJL into two equal halves. Well, the theorem states that when you draw that, these segments over here to the opposite side end up being proportional to their adjacent sides. And this is not obvious because here we do not have similar triangles that are created. KMJ is not similar to LMJ. And how do we know that? Well, we have no knowledge here of these two angles being congruent, and certainly KMJ, this angle, is not congruent to LMJ, this angle. So it's not obvious why this is. Okay, so let's see why this is true, that when you draw within one triangle an angle bisector, that it does create some proportionality. So let's prove this theorem. Here on this page I have ABC drawn. You could see that we have an angle bisector here, BD, and we're going to draw some auxiliary lines here. We're going to purposefully draw an auxiliary line CE that is parallel to AB. And we're also going to continue this angle bisector here, BD, just continue it on until it intersects that parallel line CE. And so we know that when we have these parallel lines, we create some congruency with angles. So here, definition of auxiliary line, just a helpful line that helps us understand the diagram. Now, angle ABD, this angle here, is congruent to DEC. Why is that? That is because of alternate interior angles. I'm going to use a single arc because ABD is drawn with a single arc. Alternate interior angles. And what happens here? BC, this side here, is congruent to CE. Well, if you take a look at what we just created, we've got some base angles here that are congruent. Therefore, the sides opposite those angles are congruent, so we've created an isosceles triangle. You could say the converse of base angles, or you could also say converse of the isosceles triangle theorem. And next we have angle BAD is congruent to DCE. BAD is here, and that's congruent to DCE, which is here. And again, that's on the inside of the Z pattern of parallel lines, alternate interior. And we have BDA and CDE. BDA here and CDE. And you can see that those angles, I'm going to use a line, are vertical angles. And so what did we create? We created two new triangles. One was a part of the original. ABD is now similar to this triangle here by angle, angle, angle. We've got three pairs of angles that are congruent, therefore they are similar. Now, AD, you could see the first and the third position here. AD is to CD corresponding, as AB is to CE. And the reason for that is just side proportionality of similar triangles. I'm just going to say side proportionality. And the only thing we're doing in that last line here to show that these segments here are actually proportional to the sides is we are just going to substitute. CE is congruent to BC, so that's the only thing we're changing. That's pure substitution. And hence, we can conclude that these segments across this vertex where the angle bisector originated, these segments are proportional to these sides of the original triangle. What we could do with it. So here we have an angle bisector. We know it's a bisector because we're showing that this angle is being cut into 2 equal halves. And we just learned that these pieces over here that are created, these segments on the opposite side of that vertex, are proportional to the sides adjacent to the angle being bisected. So we could say x is to 15 as 6 is to 9. And you can cross multiply and solve. Likewise, we see we have that angle being bisected again, and we know these pieces are proportional to the sides. So we could say n is to 5 as 21 is to 7, cross multiply and solve. And hopefully this helps understand these 4 new theorems of parts of similar triangles. Take care. Thanks for listening.